And we're
Great.
live.
We are live. It's great. Hey, welcome to everybody. We're so glad to have a classroom joining us, and today we're going to be talking with a gentleman, Jeff Sprenger from Xemory Software. He's going to be showcasing some projects he's working on and just kind of answering some of your student questions and that kind of thing. I got a quick little intro I want to do, though. I just want to welcome everyone. This is our Vermont Hour of Code guest speaker series. The Agency of Education, Vermont Agency of Education, is a sponsor of this. VitalLearn is one, and Vermont's Google Educator Group, which Lucy's going to talk about in a sec. My name is Peter Drescher. I'm the Education Technology Coordinator here at the state. We're joined on screen by Lucy Delabrie. You saw her a second ago. Your teachers here, Dave Hanson, Sally Bisaccio, from your neck of the woods there, right? And I think we have a couple of other folks that have joined remotely as well. Really excited that we can be doing this. The Hour of Code Week is something really exciting for schools in Vermont to do. I visited a couple schools earlier this week and really saw some engaged students. I'm sure some of you in the audience today maybe have played with some of those tools and you know, in coding and programming. And I think this talk today and this what Mr. Sprenger is going to show you today really relevant to that kind of stuff. So. I'm going to have Lucy Delabrie tell you just a little bit about the Google Educator Group. That's one of the sponsors of this, and she's been really helpful in putting this together. So why don't you give us a little synopsis of that, Lucy?
Thanks. I'm Lucy Delabrie, and I am a VitalLearn representative, and I'm also co-facilitator with Elizabeth McCarthy of the Vermont Google Educator Group. And there are thousands of these all over the world. We have our own special one in Vermont, and if you go on Google Plus Communities and search for Vermont GEG, you can join the hundreds of members who are already in that group. The reason that we're doing this is because we're trying to showcase how Google Hangouts can be used to run events and to extend your learning outside this classroom, just like these students from Southern Vermont are doing today. And so if you have any questions on how to do that and use Google Hangouts, contact the Vermont Google Educators Group, and Lucy, myself, and Elizabeth will be glad to help you. Thank you, Peter.
That's great. That's great. Thanks, Luce. We're so glad you're helping us today with this as well. Let's get right to it here. So we have our guest today, Jeff Sprenger, and I'll just do a quick little piece about how this kind of came about in this way. Mr. Sprenger was involved in Tech Jam, which maybe some of your students remember was an event that was held up in the Burlington area in when was that, Jeff? In October. Yep. And I wandered by his table. He had a table for Xemory Software, his company, and I wandered by his table, and I was struck by that Mr. Sprenger was probably much like many of you students are in your classroom right now, and very excited about the power of programming and coding, and he's really created some fantastic tools and projects around his company and what he's doing with it. And I'm just excited to have him here and share with you some of those things. So Jeff, let's start off. Glad to have you.
Okay, great. Well, thank you very much. Welcome, everybody. I just want to make sure that you can hear me. Can you hear me at your end?
Loud and clear.
All good. All right. So thank you, Peter, for the introduction. This company, Xemory Software, we started it really earlier this year, in about July. And I'm joined with, today, I have a couple of guys I want you to meet that work with me here in Burlington. Come on over, guys, and say hi. You can see them in the camera here. So on my left is Alex, and on my right is Aaron. They're both recent graduates from computer science and mathematics at University of Vermont. And they've been working with me for the last 6 months to create a game called Neurobotik. And we're going to be working on that for the next year. So I'm going to show you a little bit about what we're doing with the robots and how we're programming them in a very unusual way. And then I'm going to give you a demonstration of a robot arm that you can move around and program. And I'll also give you a link to where you can download that and play with it yourself. So the next thing I'm going to do is share my screen with you. And so that might take a minute to get that working right. And let me know if and when you can see my screen.
And we have a request to repeat the name of the game.
Okay, the name of the game is Neurobotik, and you're going to see it on the screen just in a second. Can you see my screen yet?
Not yet.
No, we'll try it again. Start the screen share.
There we go. Something just happened.
Okay.
Here
I
we
think you
go.
can.
We see it.
Yeah.
We see it now.
All right.
Yeah, we're good.
Thanks, guys. So Aaron and Alex are going back to work, and I'm going to spend the next 45 minutes or so with you. So let's just start this. Let me see what's going on. We just have to get everything working here.
There we go. Beautiful.
Okay, so you can see that? Great.
Yes, we can.
All right, so that's a little picture of one of our robots. So there's the name Neurobotik. That's the name of our game. The company's called Xemory, and I'm really happy to be part of this hour of code with you folks. So let's get started. The game is really a combination. That's the robot eye there. It's a combination of about 4 different things. Robotics, and in order to really understand and use robotics, we have robotics, we have gaming, so computer or video gaming together, and then we have evolution. So instead of programming these robots, we actually evolve them. We have populations of robots, and we choose the most fit, and then after many, many generations, we evolve robots that can walk, that can jump, and that can do all kind of different things. And then finally, we have neural networks. So what we do is we control the robots using a neural network brain. So that's a little different than just writing code. The underlying areas of study, so if you know, like, where would you learn about this stuff, robotics really has a lot of its underlying principles are in physics, particularly mechanics. In gaming, you would study computer science, okay, on the programming side, but there's also all kinds of things in gaming where people do very artistic work. There are things like environmental artists or 3D modelers and so on. So computer science, but also in the art world. Evolution has its underlying principles in biology, but also in computing. And then finally, neural networks is really the ideas come from neuroscience. So we call this multidisciplinary, which means there's a lot of different skills and people that come together to make something like this happen. Here's a picture of one of our robots. This one's name is Clyde, and I'm not sure if you can see my mouse here, but he has a round body and he has 2 legs, and what we do in the game is we give you an environment. First of all, we give you tools where you can evolve him to walk. Now, he starts out, he can't stand at all. He just flops over on the ground immediately. But after something like 50 or 100 generations, he evolves to walk. So we go through several hundred robots, and then you end up with a walking robot, and sometimes some very peculiar walks. These are some of the other robots that we're working on. This left one we call the jumper. The upper right one is a crab. The lower left one is a mouse. That's a 2-wheeled robot. And then there's Clyde again. So in each one of these, you're really evolving the motion, or what's called the locomotion, of the robot. It turns out that programming a robot to walk is very, very difficult. You need to understand all of the equations of motion of all the parts of the robot, and instead what we do is we evolve the robot, and it sort of discovers that process automatically. Here's a picture of a robot arm in an industrial environment. So this was a rather large one. They come in all kind of different sizes. A lot of the devices like smartphones and iPod touches and so on are manufactured in China, and many of them are now manufactured using these robots. The company that assembles those robots has something like 300,000 robots on order. In other words, they're gearing up toward 1 million robots. That's almost an army, right? And so robots is really a up and coming, a very big growing field, and understanding how to program those robots, to build them and design them is sort of a cool area of technology to go into. We have put together a small little game with a robot arm. I'll show you that next. So here's the robot arm. So it looks kind of like the industrial robot, and you'll see that it has a base. That's this thing here at the bottom. I'm not sure if you can see my mouse on the screen.
We can.
And then it has another link. We'll call this one, you know, the main arm, and then the forearm in green, and then this brown thing at the end is called the gripper. Now, in robot language, each one of these pieces, like the white line, is called a link, and then The dots or the circles are joints between the links. The round ones are called revolute or rotation joints. So like your elbow, let's say up here, you can move it sort of back and forth, right? But you can't really twist it around the way you can your shoulder. Your shoulder is much more flexible. It has what we call more degrees of freedom. So the more degrees of freedom a robot has, the more complicated it is to control. So this one, at the base, you'll see these two triangles. That's a twist joint, sort of twist like your wrist. So the base can move around in a circle. Then we have the shoulder joint, which is just 1 degree of freedom, the elbow, then the wrist here that can bend, and then the wrist that can twist. So we have 5 degrees of freedom in this robot, and we're going to go into this little sort of mini game and show you how we control it, and then finally, how do we use some code to automate the robot. So you should see now on your screen this kind of gray robot arm, and at the bottom is a link. And if you write that down, okay, you can do this now or you can do it later, depending on if you have a computer. But if you write the link down and you click on it, it'll open a browser and it'll bring up the same stuff that I'm going to show you right now. Okay? I'm going to move on. Can everyone still hear me?
We can.
Yeah.
Good.
Can you take a couple of questions, Jeff?
Absolutely.
I just have a question. Will you go back? Can you go back to the slide of Clyde?
Yeah.
I'm really interested. What is Clyde made out of? Is that stainless steel?
Yeah. So that's a great question. This looks like stainless steel, but Clyde is actually a virtual robot. So he doesn't exist in the real world. He was modeled in a program called Rhino, and then we applied textures to the robot. This is called a hard surface texture, and then we set it up with a couple of lights, and then we render the robot. So it looks very, very real, and it's meant to look like stainless steel or aluminum.
Yeah, that's really cool. That looks great. And I just want to, maybe this question is more for the students in the audience, but you know, when you were showing, I think the next slide, when you had the 5 different robots, the crab, yeah, this one here, you know, this is for you students. I mean, imagine if you could, that a job that you get to go and do is to create these guys in your job every day. I mean, I especially love the crab with his eyes looking up under the little thing.
Yeah, and I'll tell you a little about where the designs come from. A good friend of mine who was originally from Vermont now lives in California. He was a toy designer for Hasbro and Mattel, and he particularly designed quite a few of the Hot Wheels cars that some kids may be familiar with. So we got together about a year ago and we started talking about this and started to work on design. So his name is Kyle, and he's responsible for producing all of these very cool robot designs. And then we take these into the game engine, and then we link them up with the physics parts and the robot joints, and then we program them.
Wow. Jeff, we did get a few questions that some of the students put in the chat window. I'm looking at them and thinking you might already plan to address some of those in the presentation in your upcoming slides.
Yeah, I can go through some of these now, and then we'll go through the demo.
All right.
Dave Hansen asks, how did you come up with the game? Why did you make it? And how, oh, sorry, this is moving on me. And how did you come up with the look of the robot? So the look of the robots I talked about came from Kyle. The idea for the game really comes from a course I took here at University of Vermont in computer science called Evolutionary Robotics. And it's taught by a guy named Dr. Josh Bongard. And he is one of the world experts in evolutionary robotics.
Wow.
And he was one of the recipients of the Presidential Early Career Award from the National Science Foundation. That's a very prestigious award for some of the brightest young scientists in the country. So he's working together with us on this project, and really, you know, we thought, like, hey, this would make a great game, the stuff that we were doing in the course, if we could kind of wrap it in a way that kids could play. Some more questions. How do you play the game? The idea is that you evolve robots and then you bring a robot into a challenge. You have a certain amount of time to complete the challenge, and then you get a score. There's a leaderboard, and then you can see how your score compares with other kids. Now, we're still developing the game, so that the gameplay will change as we add more robots and more features. Is it educational? There is an educational component, and we're going to be expanding on that, where we teach some of the basic underlying physics in the game, and teach you more about neural networks and also about programming. We've got some more questions.
Is the game available now? I think was one of the ones that came
Okay, no, the Neurobotik is not available, although we have been testing it in 4 schools in the Chittenden County area. And if schools are interested, next year we'll be doing more testing. So they can contact me or Mr. Drescher and ask about how would we get Neurobotik into our schools so that we could play with it. One question was, how long did it take to make the game? The game right now has, I think, 9 levels, and we've been working on it since July. The game will have about 32 levels when we're done, and we should be introducing it by the end of next year. Is it designed to work on consoles, PCs, or phones? It's designed to work on desktops or laptop computers, either Mac or PC. We're looking at doing a version for tablets. Most likely won't run on phones. We don't think there's enough resolution on the phone for you to really be able to interact with the robots easily. Question was, is the game going to be available worldwide? Yes, it will. We'll be distributing it hopefully through Steam and also directly on our website. So we'll make it available to anybody who wants to use the game. Are you planning on releasing the robots into the real world? That's a great question. It turns out it's very difficult to take a robot that you evolve in a virtual environment and then bring it into the real world. But we do have some plans to try to create some physical robots, but that's a few years down the road. And I see from Dave Hansen, we want the game from MAUMS. So I think that's Mount Anthony. So yeah, we can talk after this. And will it be available for free, or will there be a cost? Initially, it'll be available for free. Eventually, we will be charging for the game. We have to work out a price model, and that'll happen next year. But I assure you that it won't be very expensive. It should be affordable and a lot cheaper than buying robot parts and building your own robot. Okay, so that's it for questions for now, and I'll take some more after we go through. Now, I'm going to bring up my browser. Now I'm just going to switch over and I'll move it over to the other screen. I'm not sure how fast the video rate is, across the internet, and how much you'll be able to see. So let me just go over to here, and I'm going to move this onto my other screen.
Perfect.
Okay, so you guys can see that, right?
We can.
Okay.
Oh, now we see me.
Yeah, I'm flipping some screens around here. I have 2 screens running. Okay, so I'm going to expand this a little bit. So if you go to that URL, you'll see it up here, right? That's probably really small, but it's the Xemory.com robotarm/robotarm address. This is what should come up after it loads the Unity 3D plugin for your browser. So I'm running in Firefox. You should be able to run this in Internet Explorer. On the Mac, you would use Safari. So I'm just going to right-click here, and I'm going to go full screen. Okay, change my screen on me. So what happened was I went full screen, but it wants to be on my other screen. So
right.
I'm gonna turn off my screen share for a second. Is that off now?
It is off. You're back.
Okay, now I'm going to share my other screen. All right, so now, okay, good, you see that. So we should be able to go full screen. Is it there yet? I might need to share. I'm having a little trouble getting it to do my full screen. Let me try that again. Go full. Yeah, I'm not sure what's going on here. You guys.
We could see it when you had it not full screen. It was pretty good.
Yeah. Can you maybe stretch that
okay.
a little bit, make it big?
Right. So here, let me just come over here. I think that'll work.
Can I just ask a quick question of
Yeah,
the
it doesn't
groups?
stretch.
Just Skylar, what school is Skylar from?
I'm going to unmute Skylar here a second here.
Let me try something else real quick.
Oh, I think he has to unmute himself.
Yeah, I think so. Yeah.
Let me just. I'm going to try and bring up the non-web version.
We are at Pownell Elementary School.
Oh, great. Welcome.
Okay, we're almost there. I'm going to bring up another version of this. Let me see. I'd like to do it full screen or close to it so that you can actually see what I'm doing.
So maybe while Mr. Sprenger's doing that, just as far as students in the audience there, maybe this is show of hands for us watching. But how many of you are interested in working in this kind of environment where you're devising games and working on robots, that kind of thing? How many of you have an interest in that? Just raise your hands up. Nice and high. Number of you. Yep. Mr. Sprenger, there you go. There's your new workforce with their hands raised right there.
There we go.
Coming up, right?
Coders and robot designers. Awesome.
Exactly.
All right, so I have this up on the screen.
Thanks,
I'm not sure how well you can see this. I'm going to kind of walk you through some of the components. This was developed in a game engine called Unity 3D, and so I've loaded what's known as a scene. So games are broken down into scenes, which are kind of like game levels. So you should see the orange robot arm here. There's a wall in the background, and I have a floor. There's a little red pad here called a landing pad, and I have a cube in the foreground. At the bottom of the screen, I have these little black rectangles. Those are buttons. And then I have a couple of buttons up here. So the first thing I'm going to do is I'm going to push the H key, which is for help. And you'll see it shows in the upper left, there's like numbers 1, 2, 3, 4, 5. That's keys or numbers on your keyboard, 1, 2, 3, 4, 5. And those control the different axes or the joints for the robot. So 1 moves joint 1 in the forward direction, and Q moves joint 1 in the reverse direction. Down on the left, I have C for clear. That will clear all the cubes, or I think all but one of the cubes that are in the environment. S for speed. If I press S, it changes the speed from slow to fast and back again. And the space bar will open and close the gripper. And finally, over here on the right, I have keys to move the camera around. So let's first start with the camera. I'm going to rotate around. Oh, yeah, you're getting it, right? I see.
We are, yeah.
We see it, yep. It's good.
Right. So I'll do things pretty slowly here. So I can also zoom in and out, right? Is now looking at the robot arm, but if I click on the cube, it's now going to zoom in on the cube and then back again. And then I have a second camera. If you look over here in the upper right, I'm going to click this button called View. So I'm able to have multiple cameras as is from different angles. And I'm going to have the other camera over this way. Now I'm going to move the robot. So if I move that, press key number 1, it starts to rotate in one direction. Number right here at the base of the robot. Let's just click over here and zoom in. Trying to get there. I don't know if you see that yet.
Yeah, we got it.
Okay, so you see that number, right? So I can rotate this thing 170 degrees or so. Let's take it a little bit around, and then I'll pull my camera. And then I can now, I'm going to press key number 2, axis number 2. I'm going to press the W key. I can move this up and down, right? And then here. And then I can move the gripper up like this to move the camera around so you can position this. So you can see that controlling a robot this way is going to take some time, right? Oh, I just went right through the floor there. So the idea here is that you move this around, and you can pick up the cube, which is over here. If I click this button in the upper right, I get a new cube. See, now I've got two of them. I click it again, and now I have a red one. That cube, I don't know if you can see it, is an exploding cube. So if they're red, they have a countdown timer to explode, and you only have 5 seconds to move it from here over to the pad. So now let's zoom in on the robot again. All right, so let me see, I've done this with a couple of middle schools. It takes people about 15 minutes to figure out how to control all the axes to move the robot arms around. So if you download it, you can try it. But there's a better way to do this, right? And the way to do it is through programming. And so I'm going to click, I'm in manual mode right now, that button on the upper left. If I click on that, I'm now gone into script mode. And you should see a black rectangle in the upper left corner. Can everyone see that?
We do.
You do? Okay, I'm going to click the load button, and it's going to load some script that I wrote. Right, so this language is called Lua, L-U-A,
Okay.
and it's one of the scripting languages that people use in the gaming world. So people that are familiar with mods for different games may have heard of the Lua scripting language. So what this script does is when I run it, you'll see that I'm going to highlight this first part right here in blue. And I'm sure that you probably can't read it if you're far from the screen, but basically it's a function called start. And when I click the run button up here where my mouse is, it's going to run this script, and this assigns these words or labels to the buttons, and then if I scroll down further, each button is programmed to set the robot to a particular, each one of the joints to a particular angle. So let's just click the run button, and now you should see that these buttons at the bottom all have words on them. First one's home, then there's cube 1, cube 2, pad 1, pad 2, pad 3, pad 4, and then gripper. So I'm going to click the home button first, and you'll see that robot move pretty quick. You probably didn't even, because of the video slowness, you probably didn't even see the transition. All right, now I'm going to go click cube 1. Now it's in cube 1 position. I'm going to create a new cube here. Oh, I've got one of those exploding ones. Cube 2. I probably won't get it fast enough. There, just blew up. Let's get another cube. Now I'm going to click the gripper button. Now I'm going to click pad 1. And I'm over at the pad, and now I can drop the cube down on the pad. I'll create a new cube. I'm going to do the same thing now. I'm going to go cube 1, cube 2, gripper, pad 1, drop. So if I was doing that robot by hand, it would take me, once I got good at it, it would take me a couple of minutes, or maybe take me 30 to 60 seconds to move a cube. With the programming and pre-programming these buttons, I can do it in about 3 or 4 seconds. So if you want to move one of the exploding cubes over, here, let's see if we get one. It's grip, pad 2, and then there. And once I put the exploding cube on the pad, the timer stops. So if I knock that cube off, let's go into manual mode, and I'll just move over a little bit like this. Hold on a second. Just knock it off. You can see I'm just about to take it off. Whoa. There. Boom. It explodes. So back again, let's switch back to where we were with our. So a kind of fun thing that you can do too with this, and this is sort of now the gaming I'm talking about, you'll notice that when I click a cube, it pushes the other one out of the way and it goes flying. So all of these pieces are under control of the physics engine, which is part of the gaming environment. So if I click these, and when I brought this out to a middle school, this is what some people did for like 20 minutes. They just clicked cubes and more cubes and more cubes, and pretty soon all of this stuff blowing up, cubes flying everywhere, which is kind of fun. So let's go back to the script here. I'm gonna actually, let me close this here. I'm gonna click the C button to clear all the cubes. I'm gonna zoom back into the robot. I'll put another cube down. And now I want to go look at the script. So that one's gonna blow up. Hold on. Boom, gone. Okay, regular cube. So let's look at this script. This first function really was responsible for just naming the buttons. If you click the first button, which I've labeled home, let's change that to Mount A. And now I'll do run. And now the label of the button is changed to Mount A down here. And now we want to create a different position for the robot. So what we can do is we can go back to manual mode and we can move the robot around. Let's move him quickly. So we'll start, this is our new position. We're going to use, like, say, around 3 degrees here. So I'm coming down here and I'm going to, oh, hold on a second. So I want my robot to be at 3 degrees, and the next axis says, on the robot, it says 35.5, and then I've got minus 87.5. Right, and then finally 51.7. You guys probably can't read that from there. And then it's about 0 or 0.8 on the last one. I'm going to click Run. So now if I go back to Cube 1 position and Cube 2, and I grab the gripper and I go down to the Mount A position, I go back to where I was here. So I've kind of programmed the robot to return to this position by programming what button 1 does. Now, one of the things that I noticed when we were building this is that when I grabbed a cube and then changed positions, the cube would fly out of the gripper. And so what I did was I created a button to open and close the gripper. That's button number 8. And this is the code that goes with it. Now, I know a lot of people don't write code, but basically what this code says is that if the gripper is closed, then put the word grip on the button, which is what you see down here, change the robot force to 5, and a couple of these other parameters, P and D, are the controllers. But basically it said slow down and reduce the force on the robot when it turns. Otherwise, the gripper's off, and I can kick the force back up to 20, and I can actually double my values for P and D, which are part of a PID controller. So what you can do here is you can create these buttons, and you can write whatever code you want it to. So you could have this robot go to different positions, but in the game Neurobotik, we could use this code to make the robot walk forward, or to crouch down, or to jump, or to crawl. Those are some different examples. Finally, just one thing, and if you're playing with this, I'll go back into script mode. There's a little button here called angles, and you can turn that on and off to show you all the angles on the robots. Questions, and the next thing I'm going to do is I'm going to go into the game engine to show you kind of how do we Unity 3D. But so remember that I have these labels on here, these angle labels that I can turn on and off, and you'll see in the game engine where they come from. So here, let me close this, and I can take questions now.
So we have a few of them in the chat window. And Peter, do you want to call on a couple of them?
Sure. Are there keyboard keys for pad 1, pad 2, etc.?
Are there keyboard keys for pad? No, that's a good question, no, but that would be a fairly easy thing for us to add, which would be keys for those buttons at the bottom of the screen. So great suggestion, and fairly easy to do in the game engine environment.
I have a question, kind of, and I think it goes along with a couple of questions that I'm seeing in the chat too. Is maybe Jeff, just talk a little bit about. I noticed, like, there were repetitive patterns that the robot does. So obviously, as the robot, and maybe this goes back to your piece about evolving the robot, but as you realize that there are repetitive patterns that they do, you can then use those functions to make one key for all those steps, right? And
Yeah.
students maybe just, you're listening to his answer here because this is how things kind of, I think this goes to this evolution piece that as you make it better and better.
So that's actually a really great question, because right now what's happening is you're telling the robot you want to go to these positions, but you really don't know how long it takes. And so if you wanted to do this, typically how people do this with a robot game or so on is they say something like, make the robot go forward for 5 steps, and either it goes a certain distance and then stops, or it goes certain distance for a certain amount of time. So you need feedback, okay, from the robot in order to know when it's reached its position. So you can chain these positions together, but you can only go to the next position when you've reached the current one. So for example, when you move that arm around, you may not want it to go from one point directly to another. You may want it to go through some other point so it avoids some obstacle. Okay.
Oh.
There's a couple of questions here I see.
Yeah,
is it possible to pad a red block before it explodes? Yeah, I think I showed that. Once you move the red block over the pad, it stops the timer. And as we develop this further, you'll get more points for stacking up red blocks than you will. Somebody asked if you can make a house or a wall with the blocks. That's going to start looking a lot like Minecraft, but we'll be able to stack the blocks in different forms with the robot. And another one asked, can you make buildings with the blocks?
I think we have some Minecraft players in the group.
Yeah, totally. I get it. I like Minecraft. I think they already do a pretty good job of that, so I don't think we're going to try to beat them at that game. Is it multiplayer? Currently, it's not multiplayer. It's single player, but you can share. In the Neurobotik game, our concept is to share the robots between groups and also to share the evolutionary behaviors and then compete with each other on these shared robots that you make better than the other people, and there's a leaderboard where you can see how well you're doing. Can you make your own robot in the game? Yes, when we introduce it, you'll be able to build robots from parts. What happens when you just repeatedly create blocks? I think I showed that, and the blocks were kind of, one block would push the next block out of the way, so it would spring up in the air with some force and then land. Okay, I'm going to go on. I think let's see what we are at 1:37 p.m. I'm going to go over to the game engine fairly quickly. I want to give you an overview of what the game engine looks like. So let me.
While you're moving there, Jeff, can I ask you a question? I noticed one thing. When you move the block onto the pad, and students, this may be a way to think about programming as the steps that it takes to get to where you want things to go. I noticed you brought things over to the pad, and then you turned the robot around and grabbed another one, brought it over. And when you set it on the pad, obviously another whole step that could come along in the robotics piece is how they arrange themselves on the pad. In other words, so that the robot is like always able to put it in one spot, but there's not something already in the way. Is that kind of like, when you're designing these things, how do you kind of think about, when kind of like a new problem presents itself, how do you kind of manage that in your process?
Well, this one, you bring up a very good example right now, because you'll notice that what we did was we created pad position 1, 2, 3, and 4, right? And we had to position the robot at higher and higher positions, because otherwise you'd knock the block off that you just stacked. So one of the things you do in robotics is you would want to physically move the robot arm to those positions, or at least to be able to calculate where to put the next block. And that requires, some geometry to figure that out, the position in 3D space. There is a whole branch of robotics, or there's a technique called inverse kinematics. And what inverse kinematics is that if I take that gripper of the robot and I say I want it to be here, the math figures out what all the angles need to be. And that's actually a pretty difficult problem to solve. It's not something that's easily done. It's solved using numerical methods rather than using what's called an analytic approach, which means you don't have an equation that can give you the answer. You have to sort of approach it by estimating the answer and moving a little bit at a time. Can everyone see the screen?
Yes, we can.
Yes? Okay, so the robot arm. So this is the Unity game engine I brought up. And right now you're looking at the scene mode, and you'll see that it looks pretty much like what I showed you, except I'm going to zoom in here a little bit and move around. This is actually what you do inside the game engine. So one of the things that we have a few things in here. We have a ground, which is right here, this copper plate that you see. We have some walls in the background, and then we have the robot arm. And then up here, there's this little sunshine thing, right? Well, that's the lighting. So the game, when you set it up, you need to set up a scene. You need a floor. You need some game objects, and you need lighting, and you need cameras. So I'm going to just click on the light right now, and let me move this down a little bit. And you'll see I have the sunshine here, and it's directing the light this way. Now I'm going to click on this icon to rotate the light. And as I rotate this light, you should see the shadow of the robot arm move. So you can see, like, I'm moving the sun around here, right? And I can change it. It's also affecting the shadows on the back walls. So a lot of what goes on in gaming is figuring out what kind of lighting to use. And the more complicated your lighting is, the more powerful the computer has to be that's going to play the game. Okay, so here, this is the lighting effect here. And then you'll notice that we had cameras. We had 2 different cameras. And right now what I'm doing is I'm showing you, I'm backing out, and I'm showing you where one camera is over here. And in the lower right picture, I can see what that camera is looking at. And I can switch to the other camera, and that's the back camera. That's way over here behind the robot arm. So when you're designing a game, somebody has to figure out where all the cameras are going to go and how you switch back and forth between cameras. So one common thing is if you're playing a game where you have a computer character or you have your own character avatar, there's a camera right behind you. Okay, so it's sort of over-the-shoulder camera that follows you around. So cameras can follow objects, or they can be stationary. I'm going to click on the robot now, and now you'll see, I might kind of zoom in here so you guys can see a little better, that there's all of these lines now around this robot. Well, this robot is really, it's made up of all of these different parts called meshes. And I'm going to expand my group here, my list. So right now I've got this one highlighted on the bottom. This is the base part. And then I have another part here. Then I have the base arm, right? And you'll see there's these little green boxes. Well, those are called the colliders. So even though the robot's shaped like this cool arm, it has a box, which is this area around which if anything hits it, it'll bounce off. So it's really important to design your colliders correctly. They need to be simple, otherwise it takes a long time for the physics engine to calculate things. But they have to be reasonably accurate. So if one of the blocks hits the robot, it bounces off. If you don't have a collider, the block would go right through. But you can use that to your advantage because you can create some pretty cool effects, letting things go through other objects and so on. Now on this base arm, and I don't know if you folks can see this, but over on the right here, where my mouse is, this gray area is called the inspector, and this is where we set up the hinges for the robots. And the hinges, what they do is they're controlled by the physics engine, and they have motors associated with them. So to move the robot, what we do is we apply a force to the motor. It can be a velocity, actually, a force or a torque that is translated into a velocity. So this is where some of the physics come in, but it's really not that hard if you're game programming because you didn't have to write the physics engine, that was done for you. Now finally, the last thing I want to talk about is this whole robot, like all of these pieces are combined into one thing called Xembot, and Xembot has a script that's attached to it, and that's where the programming comes in. So this script right here, I'm just going to open up the edit window, and I'm going to give you a very, very quick tour of the script. So this is different than the script that I wrote during the game. This is actually the script that controls a robot, which is really far more complicated. So you should see like a code window up now, and let me see if I can zoom in on the code or make it here. Control plus. Let's make this big here. Hold on. View, zoom. Here, I'm trying to make it bigger for you guys.
Here, while you're doing that, Jeff, I just have a question for you. So
Yeah.
what programming languages did you learn through college, and like how many different programming languages did you kind of go through?
Okay, well, I'm no longer a young guy. Not like Aaron and Alex that you met. Those guys are like 22 or 23,
Yeah.
right? So I'm like almost double their age. So I first of all, I learned in college at McGill University, which is close to here, right, in Montreal. I learned to program in Fortran and in C. So people will have heard of C before, and I learned Unix. So this is back in the 80s, folks. And then really the languages that I'm using today are C++. I've spent more than 10 years in C++, and this code here is C#, which is kind of like an easy version of C++.
Huh.
But there's many other different languages. There's probably 100 different computer programming languages. Some are really built for the web. Some are built for writing things to run on servers. Some are used to, for applications that you would write, like Java, that you might write to run on Android devices and so on. So there's a ton of different languages you can learn. They're all mostly pretty similar. So C# and Java are very, very similar to each other, for example.
Jeff, you mentioned Lua, and that was the language in that first window?
Yeah.
And
Yeah, so you see Lua right here. So Lua is a scripting language rather than a compiled language, which means that it can be written and run immediately inside another program. It doesn't require a whole compiler and a linker. So those are tools that turn programming code into machine code, right? A language like Lua that's interpreted, or a script language, is something that can run right away, and it's pretty lightweight. That's why we embed it in games, because it's easy to put in. There's also like if you're writing a game for the Mac, no, I'm sorry, for the iOS, like the iPhone, there are some rules that Apple makes you follow that really limits what kind of scripting language you can put in a game that runs, say, on the iPad. They have some very strict rules about that because they don't want people building little hacking programs into their, the iPad games. So what I'm just trying to show you here is that eventually you end up writing code. So this is code to control the robot. I'm just kind of scrolling down through here. It just goes on and on and on. But really what this is doing is the code is responding to things like pressing a button. This one here, when you click that button called angles, it'll toggle the angle display. It just turns on and off the angles. Okay. This one here called update, this runs about 50 times a second. So what's happening is the video frame rate is running, and every time you make a small, there's a small time change, like 1/60th of a second, it calls this code and it updates all the angle positions for the robot, and it figures out whether you've pushed on any keys or not. Down here, fixed update, rather than running 50 times a second, this will run several hundred times a second, updated by the physics engine. So this is calculating the position of different objects in the game. So I guess what I'm trying to tell you here is that you can do a lot of work without programming in the game. The artists can work in here to design the scenes. The 3D modelers can come in and place these objects. They can hook up the joints for the physics engine and so on. But eventually somebody needs to write the code so that when the buttons get clicked, or when you move your mouse, or when you press the fire button, the right things happen in the game. So this is sort of an overview. This is Unity 3D. It's one of the two major gaming engines. The other one is Unreal 4. Unity 3D is available for free for people that want to develop what we call indie games, so independent developer games. Small little companies can do that. If you want to use some of the fancier stuff, then you have to buy it. And and then Unreal 4, which makes some great games for consoles, you have to pay a little bit per month, and then you pay like a royalty. So these are just the two gaming engines, and what's pretty cool about it is if I go to build settings right here, is I can build this game for the web to run in a browser. I can build it for PC or Mac. I can build it for iOS, which is the iPhone, the iPad, the iPad Mini, the iPad Touch, and who knows what else they're coming out with. I guess iWatch. And then Android, so a lot of the tablets, Android tablets and Android phones, and also BlackBerry, which probably nobody there has even heard of anymore. Then there's also for the Windows Store, Windows Phone 8, and then consoles like Xbox 360, Xbox One, the newer one, PS3. There's also PS4 in here, and then PlayStation Mobile. So this game engine allows you to put your game on like something like 15 different platforms, which is really cool. So you only have to write it once, and then you just have to tweak it a little bit for each platform so more people can play your game. And that's it for Unity 3D. And I'm happy to take questions, or if we're out of time, we can wrap up.
Yeah, no, we're good. That's
we'll have
great.
you take off the share screen so we can see you during the question session.
Oh, sorry about that.
That'd be great.
Yeah, let me
And Jeff, just like maybe for the students, can you indicate to the students like if they've thought about using starting doing some programming and using some coding, you mentioned C#, C++. What's something that they might want to start, if they're interested in that, what might they start working in?
Well, I think if you want to do some programming for the web, you're going to use a language like JavaScript. Okay, that's pretty common.
Yeah.
And then you have to learn HTML. If you want to code for things that you could either run on the web, like a game, you could certainly do it in Java for the Android platform. If you want to use C#, if you want to use Unity, you would use C#. C# is very easy to use. It's mostly on the Microsoft platform, but it used to be. Now it's available on all the platforms. It really depends on what you're trying to do. Like if you're trying to create a game, I would suggest using one of the gaming engines like Unity 3D, Unreal 4. Some people use something called Coco 2DX, which is really developed by a group in China, very popular for 2D games. Coding it's everywhere. For instance, people in the university environment that want to do simulations and understand, complex mathematical formula and behavior, they use something called MATLAB. Which is a different programming language again. So there are a lot of options out there, but certainly C# or Java or JavaScript would really get you going.
What I wonder is if there are people in the audience right now, some of the students that are already playing with some programming platforms or some game development platforms, if they would share real quickly what they're using. I think some of you are using, I saw some Minecraft users. How many Minecraft users out there?
That's great.
There is a computer programming component to Minecraft called ComputerCraft, which you can use coding in your Minecraft environment. Any Scratch users out there? A couple of Scratch users. The next step up to doing some of the stuff towards Unity could be a programming environment called Stencil, which actually shows you the code, which Scratch doesn't, and then Unity, of course. Those are the three levels of progression I've seen used for students who are really at that game development level. And we'll put those in the chat. Some of the ones that I wrote down, the ones that Mr. Sprenger said, and I'm going to try to find links to them all. I even found a way for kids to learn Lua on an iPad if they want to.
Yeah, so I see a couple of mentions here. Somebody mentioned Minecraft. Minecraft's written in Java, but there are extensions to Minecraft where you can use other scripting languages to automate Minecraft as well. Unreal 4, their language is C++. That's probably going to be the most difficult for people to pick up and learn. It takes a while to become a master at C++, several years. I'm trying to think what else people might use. Somebody mentioned WebKit. WebKit is sort of an application toolkit to display the web on different web pages on different browsers. Some of the companies are moving away from WebKit. I think Apple is moving away from it. Chrome, Google has moved away, and Qt is another development environment that's also moved away from WebKit. So. Oh, and people have been doing work through Khan Academy. That's cool.
Some good ones there. Maybe students, do you have any other questions students might have? Just thinking about. Remember, we're in the midst of our week of hour of code, and I don't know. Actually, maybe I have one more question. Maybe this applies to the students too. I'm wondering what the two folks that we were introduced to in the beginning of your talk, Jeff.
Yeah.
What were the program languages that they were learning? Because this might apply for our students that are watching here.
Yeah, so they learn mostly Java here at the University of Vermont, and that's very typical in universities that they really get people coding in Java because it's an object-oriented language. So they learn some of the the better coding principles. And so when they started here, they needed to learn C#, but they picked it up very quickly because Java is very similar, and a lot of the concepts they translate between languages. So chances are, once you learn a computing language really well, it's not that difficult to go and learn a different language. They're all fairly similar. What is more difficult is that you have to understand what's called the APIs, or application programming interfaces. So you really need to understand what functions to call on the Mac, to get the program to do certain things. And those are different on Windows, and it's different again on Android. So every time you change platforms, that's the stuff that really changes. It's not really learning the new language that's hard. It's learning the platform.
Yeah. Are those two guys still sitting near you?
No, they're gone. They're back in their office. But
okay. I was just going to ask what they found themselves doing at the when they were in 6th grade that kind of brought them to the career they have now. So that's kind of interesting.
Yeah. Well, I can bring them back in here if you want to talk to them.
Yeah, that'd be great. I mean, I just think maybe just these 6th grade students may appreciate knowing what they were thinking about, which wasn't too long ago.
And I know that for some of the students, they had to leave because of our time and schedules are moving around in schools.
Okay, we got Aaron and Alex here.
Hello. Hey again.
Hey guys, so we just thought maybe it'd be interesting for you to share for a minute what we're talking to some 6th graders here down in Southwest Vermont in Bennington, and I wonder if they'd certainly like to hear what you guys were thinking about when you were in 6th grade, and what maybe were the things that happened to you over time that kind of got you to the careers you're in now today.
Oh. Huh.
Yeah. Put you on the spot, right?
Yeah, let me think about this. 6th grade, what was I thinking about? A lot of video games.
A lot of video games, yeah.
Playing a lot of, Mario Kart, things like that. Official video games. The things that led me to where I am now, that's interesting.
Take your math classes seriously, I would say.
That's good.
Yeah.
Yeah.
That was one thing.
What were math classes? I mean, what was your progression in math? I mean, was there a particular thing you really honed in on that got you excited about math, or talk a little bit about that.
Yeah. I mean, the whole pre-calc into calc, which you guys will go through the next few years, I think, if I'm remembering right, and then you can start taking physics, and I feel like it gets really interesting there.
That's great. And so you find that with all this, the physics, pre-calc things, are these things you find you're using every day as you in the work you're doing?
Yeah, we do. We definitely deal with a lot of physics here. It's a lot of fun.
A lot of vectors, things like that.
Yeah.
Stuff you learn once and then you just keep using it over and over in a lot of different classes.
Yeah. The answer to that question, right, about when are we ever going to use this, Mr. So-and-so, right?
Yeah, linear algebra and vectors is very important in game programming.
Definitely.
If you don't understand that, you do really have a hard time. That's important. And physics too, right? The mechanics.
Yeah.
Understanding force and velocity, acceleration, momentum, all of those things. They're very much part of the game world.
Mm-hmm.
We did have a question about what's it like what's your day like? Is it just sitting in a cubicle writing game all day, writing code all day? I think is one of the questions that's written in there. And is that cool? Or
That's a good question.
I'd say, like, depending on the day, we can spend anywhere from, like, 20 to 80% of our time coding. Like, some days we'll spend a lot of time talking about the code or talking about the product in general. But there's a lot of variety, I'd say.
Yeah, definitely.
And some days we spend, in the lounge writing stuff on the board, showing big diagrams of what our code does. It's all really about understanding our code and making it good.
Yeah.
And work better. And making it not messy is another huge thing.
The architecture is really important because you have to work with it.
Yeah, exactly. Like, you're writing code that you will use in a month to do something different, and you have to make sure that it's all very usable. So I guess to answer the question, it's not all sitting down writing code. It's a lot of interaction with other people who are also writing the code and all that stuff.
Yeah.
When you guys want to kind of inspire yourselves to go deeper or to learn about something new, where do you go to look for that kind of stuff? And how do you professional develop for yourself and kind of learning yourself? Like, where do you go for that kind of thing?
Ooh.
Inspiration. Maybe that's the better question.
We did for the game. We did the training, right? We did the training videos.
Yeah.
We learned the game engine.
True. And I think specifically to what we're doing, it's often I'll be playing a game and thinking about what they do right in the video game and how they're keeping people engaged and stuff like that. Like, just thinking about the games you play and how they keep you interested in stuff that may seem boring to an outsider.
Yeah.
Maybe just share, with the students here, share a few titles of video games that you play regularly, or you're impressed with, that kind of are inspiration, or in the past that have been inspirational to you.
Well, oof. I mean, I played a lot of Mario Kart as a kid, like he said earlier. Play Minecraft nowadays.
Oh yeah.
So tell them about the Fridays when we get together.
Yeah, we do something here at the office where every Friday we get together and we show off games that we think are an inspiration to us. Or games that do certain things well. So we've looked at games like Kerbal Space Program's a big one.
Yeah.
It's a game in which you should explain it. Like, it's.
You can kind of build rocket ships from parts and try to go to different planets in this simulated solar system, and it's a lot of math behind the orbiting the planets and getting onto the moon and not crashing.
It's not an easy game.
Yeah.
That's a very cool game.
That's great. Maybe just show of hands from the students sitting down in Bennington there. How many of you have heard of the video games that these two guys are talking about?
Oh wow.
Yeah.
There's some excitement there. That's great.
Yeah, that's awesome.
I think we're kind of getting to the end of our hour here, and I want to honor people's time because you guys have to go back to work, right? So, first of all, just want to thank you so much, Jeff Sprenger, and you two guys. Thank you so much for joining us today. It's really exciting work that you guys are doing. And as I said, maybe some of the students in that audience down in Bennington and the other classrooms that are on here, maybe their resumes will be coming across your desk one day to work with you guys as you continue doing your work with robotics there. I certainly want to thank my colleague Lucy Delabria. Thank you so much, Lucy, for helping set this up. And the other folks that have joined in, I see some other classrooms there. Dave Hansen, Sally Bisaccio, thanks so much for putting this together on such short notice. I should add. Great, there's the student. That's fantastic. So, anyways, so we hope that you'll go back to your, back in your hour of code week. We still have today, the rest of today, maybe, and tomorrow. So hopefully you're still taking part in that, and we can see you. Make sure you post things to our Think About. I'm sorry, I'm going to forget. Think About Coding blog that Lucy set up. Make sure you post some pictures there, and so glad we could have this with you all today. So have a great afternoon, everybody.
You too.
Thank you.
Thank you.
Yeah, you bet. Thanks.